Current status from the provided data, asterisk temperature, 27.50 degrees Celsius, which is slightly higher than the ideal range for most plants, potentially risky if the plant is sensitive to heat, humidity, 88%, which is much higher than the optimal range, potentially indicative of waterlogging or high moisture levels around the plant. Asterisk threats, the close proximity to ideal conditions, unhealthily cold or too hot, unhealthily dry or waterlogged, could suggest the plant is showing signs of stress, such as overwatering or lacking light, or perhaps not receiving enough water under high humidity conditions.
Hi everyone, this is AI-powered project on plant health monitoring system. Here we'll be integrating camera, vision, and temperature and humidity sensors. We'll be drawing the inferences using Llama 3.2 Vision model based on the temperature, vision, and the humidity values. At first step, we'll be receiving the temperature and humidity sensor values from DHT11 using ESP8266 microcontroller. Then we'll receive and store the temperature and humidity data from ES8266 and set up the Flask server. Parallelly, we'll be receiving the live image feed of the plant using the IP webcam Android app, then integrating the temperature and humidity values and the IP camera. We'll be passing this value into Llama 3.2 Vision model. The Llama Vision model analyzes the health of the plant and provides feedback to the user. Then the output of the Llama response is again converted to speech using Pi TTS model. This is a brief wiring diagram of ESP8266 DHT11, and in this case for powering up I'm using the power bank here. Typically we can use LiPo batteries like 18650 mAh or a 3.7 voltage battery. For our project I'm using a power bank as a source. In the left you can see that the VCC of the DHT11 sensor is connected to 3.3 voltage pin of the A266, then data pin of the DHT11 to D2 pin, then ground of the DHT11 is connected to ground of ESP8266. To the right you see the physical connections here. Other industrial use cases. To set up the IP camera from the mobile device, go to the Play Store, download IP webcam application. Once downloaded, click on the three dots and install the server. Here you will get IPv4 address. Note it down. We will use that in the Python script. Next, we'll look into the Arduino ID code to receive temperature and humidity sensor values from DHT11 and like receive it from ESP8266. As a first step, install Arduino ID. Then go to File, Preference. Make sure to enter this URL as an additional board managers. This is for A266. Then after doing that, go to Tools, Board. Here you will see ESP8266 option here. Now you have to select node MCU 1.0 ESP12 module here. Next, we'll be installing the required libraries. Go to the library tab here. First install the Arduino Unified Sensor library, which I have installed here. Then install DHT sensor library, which is also installed here. Now we'll dive into the code here. We are setting up HTTP to send the sensor values to the computer which is connected where the controller and the computer are connected to the same network. Here enter your SSID and a password. Then DHT pin, which is GPIO pin. For reference, this is how it looks. Earlier we have seen that we have connected the data pin to D2. D2 is connected to GPIO4 of the ESP8266. So that's why I entered it as 4 here. Now DHT type is DHT11. You can use DHT22 also. Then you have to replace this with the IP of the computer by running the Python script. To do so, go to the command prompt and type ipconfig. Here you will be receiving the IPv4 address, so replace with that here. Then we'll be calling the Wi-Fi client. We'll be connecting to the Wi-Fi here. Initialize the DHT sensor. Read the temperature and humidity values. check if the readings are valid, print data to serial monitor for debugging, just in case you need. Then connect to the server, send data as HTTP GET request. So after doing that, we'll be flashing the code into the controller. So for this, go to upload. It is compiling the sketch. Make sure to press the flash button, which is shown on the screen here. So here will be getting an option like a log mentioning writing at the address. Wait for the code to get uploaded. Now the code is successfully uploaded to ESP8266. Make sure to press the flash button, which is shown on the screen here. So here will be getting an option like log mentioning writing at the address. Wait for the code to get uploaded. Next, we will enter into creating a Flask application that can serve as a lightweight HTTP server to receive temperature and humidity sensor data from ESP8266, and then we can store it in the database for our consumption. In this case, I'm storing the sensor value in the text file. In production grade, this won't be used. For demo purpose, I used it, and these are some data storage and communication options. We can go with database, lock mechanism, shared memory, message queues, and in-memory cache. Now we'll be setting the rate limit to avoid frequent data updates. Writing the file to the sensor value to the file, which is text in this demo purpose. Decorator, Flask decorator. Then Flask decorator to fetch the temperature and humidity values from data. Make sure you enter the CM name like your data. So we'll be getting the temperature and humidity value and writing it to the file, some print statements. It's a simple Flask application. Next, we'll get into the main application where we'll be passing the live stream image, the temperature and humidity sensor values to the Llama-3.2 Vision model and ask for the inference and predict the yield status of the plant. First, we'll be setting the grok API key. To do that, go to console.grok.com/keys, create API key, enter a display name, then you'll be getting the API key. Enter this key in the .env file. Then initialize the grok client, initialize the text-to-speech engine, where you can set the adjust the rate of natural speech and set the volume. Get the live camera feed from this URL, which we saw in the IB webcam. Read the sensor data.txt, where the Flask application stores the temperature and humidity values. It's an OpenCV video capture. This function encodes the image to base 64, which is basically the live stream image. We are converting it to the base 64. Read the temperature sensor values. Do some cleaning by removing the unwanted characters. Convert text to speech with interruption. Function to reset TTS engine after interruption. Function to quit the application and restart it. So when S is pressed, it sends the current image, temperature value, humidity value to the LLM. If Q is pressed, it quits the application. R would interrupt the ongoing text-to-speech, then wait for user to enter, send, quit, or interrupt again. We'll running it in the while loop, get the image feed continuously. When Q is pressed, the Windows exited. When S is pressed, image is sent to Llama model, reading the sensor value. Now we are sending the image and the sensor data to the Grok API. We're choosing the model Llama-3.2 11B-Vision preview. Here we'll be entering the prompt, which is what is in the present image. Here the sensor data, which includes temperature, humidity. In the present image, if there is a plant, analyze its health based on image, temperature, and humidity. Tell if it's optimal for healthy. If unhealthy, tell what needs to be improved based on temperature, humidity, and how to achieve it. Then we are giving the input image URL, the actual live stream image of the plant. We are setting temperature to 1, maximum tokens 2024, top 1. We extract and clean the response that we get from the Llama. We're calling the text to speech function here. When R is pressed, it would interrupt the ongoing TTS and restart the application. By this, we are sending the real-time image, temperature, humidity value to the Llama vision model, getting inferences on health status of the plant.
Analyzing the provided sensor data, the temperature is 27.50 degrees Celsius and humidity is 88%. To evaluate the health of the plant based on the image, temperature, and humidity, we can use the following general guidelines. ####plant health and parameters. Ideal temperature and humidity for most plants. Optimal temperature, 20 to 25 degrees Celsius for most plants, depending on the specific plant species. Some can tolerate higher temperatures. Optimal humidity, 40 to 60% relative humidity for most plants. Again, specific plant requirements may vary. Current status from the provided data, temperature, 27.50 degrees Celsius, which is slightly higher than the ideal range for most plants, potentially risky if the plant is sensitive to heat. Humidity, 88%, which is much higher than the optimal range, potentially indicative of waterlogging or high moisture levels around the plant. Plant health observations. Leaf and stem condition. The image doesn't provide clear views of the leaves or stem, making direct health assessments difficult without further details. Root system. The environmental controls, temperature and humidity, might impact the root system's health if the plant were underwatered or flooded due to high humidity. Threats. The close proximity to ideal conditions, unhealthily cold or too hot, unhealthily dry or waterlogged, could suggest the plant is showing signs of stress, such as overwatering or lacking light, or perhaps not receiving enough water under high humidity conditions. Recommendations for improvement based on the data. 1. Adjust temperature. If the plant cannot tolerate the current temperature, consider moving it to a cooler area or implementing a temporary cooling system if necessary. 2. Reduce humidity. Ensure good air circulation around the plant to reduce humidity levels. Consider placing the plant in a drier part of the house or using a dehumidifier to lower the humidity. 3. Adjust watering. Be cautious with watering under high humidity conditions to avoid overwatering. Check the soil moisture before watering. 4. Provide light. Ensure the plant receives enough light. Lack of light, combined with other environmental stresses, could lead to unhealthy or dying plants. 5. Monitor and adjust. Continuously monitor the plant's response to adjustments in environmental conditions. If the plant shows significant improvement or if environmental